weather page and you'll see Planet Watch. And so, of
Or
course,
just
as you see from the letter.
Or just check it out in the library, right over in the periodicals
There you
section.
go.
You can just go right over there.
And as you can see from there, he's a colleague
You've
of
probably
Thomas
already
Gillen.
checked this out, yeah.
So we're very
yeah,
happy to have
sometimes,
you here
yeah.
at the library.
Besides the Planet Watch,
Probably do it for
there's
others
Ask
as
Tom
well.
questions that are regarding astronomy. And this happens to be my favorite one. This one right here.
And let me also remind you about a few other things that are coming up. Since you are here as a student, we have a movie night coming up this Friday. We're showing Cars 2. We're never too old for the Cars movies. It's pretty fun. It's good if you like Mater, you're really gonna like Cars 2. So that's coming up Friday night at 7 o'clock, right back here in the meeting room. And this Sunday afternoon, we have Bell Sonore Chamber Group music for your entertainment at 2 o'clock in the afternoon. And all the other programs that we have coming up are listed in the newsletter. The winter newsletter will be coming home in a couple of weeks, so watch for that, and then you can register for programs for December, January, and February. All right, well, I have said my piece, so now we'll turn things over to Mr. Joyce. Do you need me to adjust the lights at all, or will it be good?
Lights down in front. They can be on and back.
Should we turn them
We prefer if they not be on.
back a little bit?
Yeah. Astronomers do it in the dark. Thanks.
Is that okay?
Okay, that'll work. Yeah, thanks. Okay. All right. And in fact, a little bit more particular, the Triton College does have a small planetarium theater called Cernan Earth and Space Center, and that's where I'm stationed. Named for the last astronaut to walk on the moon. We're coming up on the 39th anniversary of that event. That's almost scary to think about. Nice. Okay. Anyway, Tom does have me answer the astro questions for the Ask Tom Why column when it's pertinent. There's a fair number of questions that come up for it. So this happens to be one of them. This was April of 2006. Okay. Now, this is what our program is all about. Me, and that's what we looked like about 4.6 billion years ago. Yeah. Collapsing dust and gas clouds, forming eventually the sun, the planets going around, the moons going around the planets, the comets, the asteroids, the meteoroids, all the flotsam and jetsam making up our solar system. So, by the way, this picture was taken with a scope out near Galena, and in fact, I have a picture of the scope that actually took the shot. A little later on, we'll get to that. Okay. Anyway, we're just going to go back 11,000 years. Okay. I don't know whether any of you have visited this place. Okay.
I've probably been through there and didn't even know it.
Okay. Well, the scablands of the state of Washington were canyons that were carved out in a matter of hours. Right, hours. Yeah. It was a catastrophic event that occurred about 11,000 years ago. Now, all those boulders down there, they didn't originate there. They came from many, many miles away. In fact, I have a picture of it. But some of them weigh as much as railroad locomotives. How did they get there? And you can see more of the scablands there, and there's a waterfall right there in the front. There's no more waterfall, right at this moment, but back in very ancient times, there was a waterfall there. Here's the scablands. Let's see if I can conjure up yeah, there we go. I gotta do it this way, don't I? I gotta get my orientation right. All this gray area is all carved out. It's a very extensive region, as you can see. They're all carved out. What happened was these glacial lakes, Missoula, Spokane, and Columbia. Okay, all these lakes were originally just glaciers. Okay, now as the last glacial expanse, the last of the ice ages, the Ice Age, as we refer to it now, the glaciers melted. Got that? Okay, good.
Thanks.
That'll work, yeah.
All right, sorry, I can turn this on.
No, the wrong
It's
one.
not gonna work.
No. That's okay, thanks.
Fine,
I think we're fine, yeah. Anyway, all these glaciers melted from the center outward. And so they formed great big lakes. And at the edge of them were ice dams. But it got too warm for them. And all of a sudden these dams broke. And all that water, which was in higher up regions there, that's just the western side of the continental divide there, all of a sudden gravity is going to take all that water and send it crashing through into the lower elevation areas. And it came out roughly 1,000 feet high and going 60 miles an hour. That's what carved out all those scatlands there. So we can tell, though, that those great big boulders were not carried by the water. Any hydrologist will tell you that you can't, as strong as water can be, and as fast as it can get, as powerful as it can get, it can't push a railroad locomotive. So what happened? These rocks were actually chewed off by the big remnants of that glacial dam, which was now broken. And each of these acted as rafts. Each of these broken off pieces of ice are now charging down through that opening up valley, and where they get to a resting place and melt, the rocks that were on them stayed there. That's how they got transported. So they got transported on ice rafts. There's no other way they could have gotten there. It's kind of weird. But anyway, so anyone looking at this would say, it's the end of the world. This is really crazy. Of course, there wasn't much civilization in that region at that time, not 11,000 years ago. So, but the last glacial maximum kind of maxed out about 18,000 years ago. It started more like 100,000 years ago, but it maxed out about then, and then began its retreat, and everything became very, very sudden 11 to 12,000 years ago. And so we can see here, oops, there are some regions that are land, including up here, especially around the Gulf of Mexico, because when we're trapped in so much, whoops, doggone it, I need to go backward again. Yeah. When so much of the oceans are trapped now in ice, the sea level goes down. So that's why there's more land mass showing up here. And of course, as the sea level goes up, then all that what was once land mass now starts to disappear. So it just so happens that there's still after effects you can measure. Now, why did I choose this for the Mediterranean Sea, where the western end of the Mediterranean Sea? Because the Atlantic was rising back 11,000 years ago very rapidly, and water shot through the Straits of Gibraltar there from the Atlantic into the Mediterranean. But it just so happened that the Mediterranean was a lot more salty. It was a lot more briny than the Atlantic was. So that explains why I'm showing U-boat sinkings here, because still to this day, the Mediterranean is still slightly more salty and denser. Therefore, that water goes down and tries to go out. The Atlantic water comes in from west to east, but at a higher level. the German U-boat commanders actually knew that that was the case. So they could run their U-boats through that narrow strait without turning on their engines. They could run silent. So you get through that slot. Now a lot of them were sunk in that area anyway. But they could get through that slot without being detected. If they wanted to go from the Mediterranean to the Atlantic, they simply went down farther. They would simply submerge just a slight amount if going through the other way, from the Atlantic to the Mediterranean. So this effect is still going on. Yes, Jim?
Dan, I had heard from some other publication or video I saw that at one time the Mediterranean seabed was dry.
Yeah.
And that there perhaps was even a land bridge between Spain and Africa.
Yeah,
You
actually
happen to
there was.
recall the possible dating on that?
It had to have been more than 11,000 years ago. Yeah. Yeah.
So perhaps one of the great floods
Yeah.
was due to the dam
Yeah.
at
Right.
Gibraltar
Right.
breaking loose.
Yes. So that's the western end of the Mediterranean. Now we're going to go to the eastern end, and this is Western Asia Minor here, and you can see that the water would have crashed through the Dardanelles, across the Sea of Marmara, and up through the Bosporus, and that body of water just in the upper right corner is the Black Sea. Back then, it was there was a freshwater body there, much smaller than the Black Sea. But as the Mediterranean, now spilled over from the Atlantic, is now crashing through there, and it's created the Black Sea. So this is all happening in a matter of maybe just months taking place. So this was again, a very catastrophic event. So what do we have here? Well, people would have thought, again, this is an extraordinary event. Is it the end of the world? I mean, you have the sea level rising crazily. Glaciers were actually retreating 4 to 5 miles a year. Yeah, we don't see retreat like that at all nowadays. So 4 to 5 miles. These glaciers are sometimes twice the size of the downtown skyscrapers. Twice the size of Trump Tower, say. So these are catastrophic events. This is all that melted water, and it's just crashing into the oceans and raising the sea level. So what happens though if everybody everyone who's seeing this could somehow connect and communicate with each other? We would have to pretend, of course, that they all had cell phones. Well, if they did, and they're hearing all this, would they think this was the end of the world? So, would they think it's caused by us? Are we doing it? Are the humans doing it? Actually, our population was actually expanding at that time because there was more available territory because there's less glaciation over the land masses. So, well, maybe not, okay? Maybe not our campfires. But I'm going to insist, okay? I'm going to get on that cell phone and I'm going to say it really must be us. After all, we've got, look at this. We know we have no more Irish elk. We have no woolly mammoths. We have no mastodons. We have no saber-toothed tigers anymore. They've all gone extinct. What could have caused that? Okay. Well, warming of the earth. Campfires? Well, actually, forest fires do way a lot more. Okay. So it's not. But how would you prove me wrong? There's the question. How would you? Well, there's a way. Now, that white speck there is the Earth as seen from the Voyager 1 spacecraft when it reached the orbit of Pluto. You're talking about 3.5 billion miles out, okay? Now the Earth looks like that tiny little thing. By the way, that glow in the background which goes up and down, that's the so-called, that would be the so-called zodiacal light. That's the basically all the dust and meteoric grains of material in the solar system. When some of that bumps into our night sky, we see it as a meteor. Okay, so that's the dust grains, the combined light of them. Okay, now we might think that, okay, it's they're alone in space. How in the world can that be affected by something out there? Well, some might think that, okay, if it's that isolated and that lonely, the climate must be influenced by us humans. We're the ones causing the changes. No, maybe not, okay? Now, besides you guys, anyone recognize that? No, Jim, no, I don't want you to answer that because...
I'm just coughing.
Oh, okay.
And you ladies think, my first reaction would be the moon because it's white, but it doesn't have a lot, it's only one crater.
Okay. Actually, this black spot here is the planet Mercury as it passed in front of the sun in November of 2006. Yeah. And this sunspot up here would be about the size of the Earth. Look at how much bigger the sun is compared to the planets. Right. So the sun is not that nice little white little ball in the sky that we see. It's extremely large. It's just that it's so far away. Yeah. All right. So now there's something else there too, and that is, anyone?
Jupiter.
Jupiter, right? Yeah, that's the planet Jupiter, and it weighs 317 times as much as the Earth. Yeah, and even though it never gets closer than about 375 million miles, it can influence us. Okay. In fact, right now it's at that distance from the Earth. It just passed its opposition point. So that's about the distance from the Earth to Jupiter right now. Now, just to do a little bit more introduction of who I am. No, that's not me. But that's the guy in the telescope that took those pictures. Okay, the picture of the sun and the picture of Jupiter. Right. His name is Dr. Donald Parker, and he's stationed a little over 12 miles south of downtown Miami. And that's his telescope. It's a brute. Yeah, it's a big scope. And I'm happy to say that I made the primary optics for it. See? So I kind of helped out there. I like to think it's super sharp because I made it. Okay.
Dan, I
Yes.
gotta wonder, why is he only 12 miles from Miami?
Actually, he's got a nice place there, and what his idea of going there was the fact that there are canals there, and he can get his 29-foot sailboat out into the ocean.
Yeah.
Right.
The light pollution's gotta be worse.
It's bad there, but he's only interested in shooting the planets
Which are bright, yeah.
and solar system objects. So he doesn't worry about it. Well, he does worry about it a lot. And just as long as you brought up that point, Hurricane Andrew did $400,000 damage to his house. Yeah. It also knocked out the power. And all his neighbors came by after everyone was allowed back in, and they're all looking up and they're wondering, what is that thing in the sky? Oh, that's the Milky Way. Right. They didn't know. They don't know because it's too glared out. So yeah, that's the scope that took those shots. You'll see a little bit more of this action here in a little bit. Now, he's a retired as chief anesthesiologist at Mercy Hospital in Miami. And of course, the anesthesiologist is a guy you really rely on. You don't want to feel the pain when you cut operation, your surgeries, surgeons going through you, and well, you don't want to feel that. But at the same time, you do not want to stay in that state. You want to wake up again, see? So you're looking for reliance here. And so they wheel you into the operating room, and you're getting all nervous and worried, and so they stop you, and then you know, the anesthesiologist is going to be there, and you look up for some reassurance, and there's your reassurance. He's a little bit of a prankster. There you go. Sorry, folks.
Childhood nightmare.
Anyway, yeah. So next time you're in Miami, don't have to have surgery. All right. Okay, let's move on. Whoops. Okay, it says 3 time scales of natural climate change. What we call epochal, the longest range, millennial, which is the intermediate range, and century decadal, the short range. But what we're going to concentrate first is on number 2, because that does explain why the glaciers did go away, okay? Or at least the continental glaciers. There's still residual glaciers, though, climate on millennial scale. And here are a couple of names involved in some of the study, some of the original study. Some of you may recognize that name on the bottom, UJJ Leverrier, as the discoverer of the planet Neptune. By the way, it was discovered 165 years ago. And Neptune goes around the sun every 165 years. So Neptune just made it to 1 year old after its discovery this year. So it was discovered in 1846. Okay, so what they were doing was trying to figure out what we call orbital perturbation. Now that's a kind of a crazy word, but it simply says the planet Uranus, which had been discovered some 40 years earlier, the motion was apparently not in accordance with Newton's laws of motion and gravity in the early 19th century, specifically around the year 1821. Up until that year, Uranus was moving a little faster than what Newton's laws would have said. And after that year, a little slower. So what was doing that? We didn't know, nobody exactly knew, but they hypothesized that maybe there was another planet beyond there. Okay? So there's another planet out there. And as a result, as they're thinking about this, Adamar himself hypothesized that Jupiter has sufficient influence on Earth's motions to affect the climate on a hemispheric scale. Here's what he was realizing. The Earth doesn't go around the sun in a perfect circle. So there's a closest approach to the sun each year, and there's a farthest point each year. Right now, the closest approach is in the first week of January. I know that's a little hard to believe since it's cold then, but for the southern hemisphere, actually it can get pretty hot. And the farthest point is in the first week of July each year. But that isn't always the case. Because of the influence of Jupiter, there's a wobbling effect and a pushing effect, and the point of perihelion is not exactly the same each year. It kind of rotates around the positions that we see here. Now notice that this depiction not only has the 12 signs of the zodiac, it has that funny constellation Ophiuchus in it too. And people were all scared earlier this year about, what's this new sign? Well, actually, it's an artifact of the way they drew up constellation boundaries. It has nothing to do with it. And the shift is simply because of this precession. It's not really a shift, it's just a gradual motion, very gradual motion, which, well, takes it actually 25,700 years to go around once. So eventually the spring equinox, which you can see there is in Pisces at the top, it's shifting toward Aquarius, which explains that song, The Age of Aquarius. Right? Harmony and trust, simply and trust abounding and all that. Well, okay. Eventually it'll happen, right? Okay. I'll believe it when I see it. Okay. But anyway, we have these precession effects. So that means that although now in the northern hemisphere we're farthest from the sun in January, in July, and closest in January, that eventually will shift. And about 11,000 years from now, it's going to be reversed again. Notice that 11,000 year mark. Yeah. Something about that. Now, it wasn't enough, it was still not sufficient to explain everything. And a Scotsman working around the time of the American Civil War noticed that Jupiter would have other effects, and notably that the degree of the eccentricity of the orbit of the Earth would be also under the influence of Jupiter. So variation of the degree of the eccentricity, how much of an egg shape it would be, or come back to a perfect circle. Never comes to a perfect circle, but it does change from more egg shape to less egg shape, and more to a circle. Again, another Jupiter variation because of Jupiter's tyrannical influence, because it does weigh so much, it's so massive, it's able to do this. It does it to all the inner planets, in fact. And we can see, in fact, that as far as eccentricity is concerned, Mercury and Mars have quite a bit. Now, the dotted lines represent perfect circles. Notice the Earth doesn't get far out of it. The blue is the Earth's orbit, and the black dots again where the blue is where the Earth actually is. The dotted line, the dots are where a perfect circle would be. Now Venus isn't even depicted because it's so near a perfect circle. There's almost no disconnect. But that's transient. That doesn't always happen. Okay, so degree of eccentricity. Notice Mars has a very strong degree of eccentricity, and it's related to the fact that in 2003 we had a super close approach of Mars. Again, Mars is not perfect, does not stay in one perfect degree of eccentricity. It does change over great periods of time. And so the Earth was able to get very close to it back in the last week of August of 2003. Here's the guy who put it all together. Working just after World War I in Eastern Europe, Lieutenant Milankovitch was the one who figured out the last piece of the puzzle. The work of Adamar and Kroll still hadn't quite made the predictions. In fact, Adamar was working at the time that the first evidence of continental glaciation was being found. And the thought of an ice age was just beginning to dawn on scientists around the time of the American Civil War. So, as they looked at the record, they noticed that neither Adamar nor Kroll's predictions would have been correct. Here's the guy who figured it out, because there's still one more thing that has to happen. The Earth also changes the degree of axial tilt. It's pointing toward the North Star right now, but it can change from 22 degrees to 24.5 degrees. And when it's not tilted very far, when it's more like 22 degrees, the regions around the Arctic Circle do not get warmed up. When it's more tilted, those regions can get warmed up by the sun. And right now we have a tilt, you'll see in the textbooks, 23.5 degrees. It's right now at 23.44 degrees, and it's getting less and less with time. So we're going a little bit more toward less solar energy around the Arctic Circle, or in the Antarctic Circle as well. So back, however, at the time that the glaciers melted, the tilt was quite favorable, and these regions were warmed up. Milankovitch was the one who realized that that's the region that has to be warmed up. And so the ellipticity, the obliquity, the amount of tilt, the precession will wobble, and you end up with what we might consider roller coaster climate here. The precession is the top, the amount of tilt is the middle, and the degree of eccentricity is at the bottom. Okay? Now, what has to tip it over is the precession has to bring it to a little bit, the Earth to a little bit closer point during summer for that hemisphere to prevent ice. But if the tilt isn't strong enough, it won't do it anyway. And the degree of eccentricity also has to be strong enough to allow that precession to occur. Okay, so I'm going to point out, we are here. Let's see, come on. Where's my cursor? Curse my cursor, there we go. Okay, this is now, and this is so many hundreds of thousands of years ago, and this is into the future. So if we look at the record, we notice that here we had time where the eccentricity was so strong, you could see that the forcing effect from precession was stronger back then. So it allowed for even warmer conditions. Here it dipped, here it came back, here it dipped, and here it has come back. Notice out in the future it isn't going to come back very far anymore. So the amount of precession effect is lesser also, because there's less eccentricity. If it's not as egg-shaped, then the position in the orbit counts for less. But it still counts for quite a bit, even in our era. Come on back, okay. In our era, it went like this. So this is what triggered the ice to be removed. We were at the bottom of that cycle, which favors northern hemisphere, by the way. We were at the top of that cycle, and we were near the top of that cycle. That's what kicked the glaciers out. That is what kicked the glaciers out, see?
Dan?
Yes?
Why are we permanently altered in the eccentricity and precession areas here? Why will it never repeat the kind of behavior it had earlier?
That's because it's not only under the influence of Jupiter, it's also under the influence of other outer planets. It has a very, very strange rhythm. If you ever saw Mars' rhythm, it's obscene. I mean, it's in the, not only in the tens of thousands of years, it's all superimposed over a period that is in the many tens of millions of years.
Eventually it will repeat.
Yeah, it will repeat, but it's in many, many tens of millions of years before you get a repetition. But there's a problem with that, which we'll get to in a minute, okay? So you can see that there's always going to be changes. There's always going to be changes here. Okay, yeah, emergence into an interglacial period was 11,000 years ago. Before that, it was all icy, okay? And then we emerged into the interglacial period 11,000 years ago. But we have to be wary, because interglacial periods, on average, only last 11,000 years. So are we going to go back into the ice? Good question. Okay. Now here's some residuals from ice ages. Greenland and Antarctica are so close to the poles. In fact, Antarctica lies right over the South Pole, that they're almost never going to shed their ice. It's very, very difficult to shed the ice there. It's very, very deep. You can see elevation in meters, anywhere from almost 3,000 feet in Greenland to about 4,000 feet in Antarctica. And notice Antarctica is a much larger territory. You can see that up here. Yeah, Antarctica spreads over much larger territory than Greenland does. But the Arctic has an ocean over it, whereas a landmass dominates the southern polar region. So this thing is going to not ever disappear. Believe me, it's not going to. Okay, what we call climate on the epochal scale. This is a much longer period. Tectonic forcing involved. Continental drift. Okay. Now, what we're showing here is the continent called Gondwanaland, which eventually split apart to form South America, Africa, Antarctica, India, and Australia. Yes?
How did they get that name, Gondwanaland?
You know, I'm not exactly sure. It's possibly a result of 113 proof old granddad, you know,
Okay.
something like that. But
Wasn't
we
there
could,
another name for the Earth with all the continents
yeah, there was
when
there
they
was
were all together?
there was
I forget what they're called. What they
Or it's
call it.
Pangea.
Pangea, right?
That's right.
Yeah, and Laurasia. Yeah. So besides Gondwanaland, there was Laurasia, and the two together formed Pangea. That's correct. Yeah. That's where we're at. Now notice that fossils from these extinct creatures were found connected, even though they're on separate continents now. The fossils are found from all these regions, and therefore they were connected. Yeah. And here's how it was. They were all fairly far south and kind of in the icy regions. So when we look at the result of glaciation, the moraine regions and the erosion, we notice that the erosion is in all those areas there, the white regions here, on all these continents. Where's my cursor? Come on, right? Okay. Well, okay, cursor's not coming this time, but you can see that South America, Africa, India, Australia, all have terrain that is highly suggestive of glacial erosion on a massive scale. But they've drifted since then. So tectonic forcing has changed the regime. But that occurs on a very, very slow scale. A very slow scale. But now the contemporary regime is like this. The oceanic currents cannot go through the Panama Canal. They can't pass through the Isthmus of Panama. So they're kind of stuck, unlike about 40 million years ago, when the Americas were still separate. And they've been closing the gap ever since, and about 15 million years ago, the gap was closed completely. So instead of having a nice constant warm current going through and very little current activity coming from the higher latitudes, whoa, here we go. Since the Labrador current coming down through here, this is the so-called Humboldt current and the Peruvian current, which allow, oops, I didn't, go back, okay. So, okay. Well, anyway, these currents now not only allow colder, high latitude water to come up toward the equatorial regions, they also, as they scrape along coastlines, they tend to create upwelling of deeper, colder water. And as the Humboldt current becomes fairly strong and pushes the equatorial water away from South America, then that particular area gets cool. We call that the La Nina. When it isn't doing it, then we have El Nino. And basically what's causing that is the trade winds. The trade winds, when they're strong, you have a La Nina effect. You get the colder water to come across the Central Pacific. And when the trade winds are more subdued, oh thanks, okay. I know mine isn't working real well, okay.
Well, that one's fairly dim too, but
Okay.
I think you can maybe use
You know what? I'm gonna try mine anyway. It's over here. Yeah. Yes.
Are you gonna be looking into,
There we go.
looking at things like pole shift in this talk?
No. No, we're not gonna get across that, and there's no time.
Yeah, okay.
All right, so we have currents here that come up, not only come from the the higher latitudes, they're actually forcing upwelling of colder water. So as the trade winds run across here, they're able to push more and more of that water away from the land and out farther into the equatorial regions. So we have cold water developing there, whereas in ancient times that didn't happen. In fact, in our show at the Space Center called Dinosaur, the opening line is, 100 million years ago, the Earth was very different than today. The climate was warm and wet. It was like summertime all year long. Yeah, that was true back then. But because of these strange regimes of colder water coming up toward equatorial regions and cold water coming from down here and again into equatorial regions, what happens is you get colder air. You get colder water at the surface, it chills the air. But that wasn't the case all the time. Okay. Now, what we're going to call recent geologic history, and really tongue-in-cheek saying this, because we're going back 600 million years. Okay? 600 million years. So in other words, today's date is at the extreme right corner here. And this is very far back. Look at the temperature. Cool compared to, here's the age of the dinosaurs, the Triassic, Jurassic, and Cretaceous. And even well into the Tertiary, the age of mammals, beginning at this point, it's still fairly warm. But like I said, about 40 million years ago, the gap between the Americas began to close. And by this time, they had closed down completely. And that's when continental glaciers began to actually roam across the continents, was then.
What do you mean by the gap between the Americas closing?
In other words, the Isthmus of Panama, it was actually open in very ancient times. So
Okay.
water was able to flow through there freely.
All right, got it.
Yeah. But now it can't. That's why the currents of today, the modern currents, have to do all this wheeling around, and they're forced then to bring up upwelled water, which is cold, and also they're going to bring water from higher latitudes, which is colder, into the equatorial regions. So that's where we have a problem now. You might call it a problem. I'm not sure you can really call that a problem, but it's cool right now. So glacial ages also occurred here, even in the midst of the age of dinosaurs, not for a real long time. And then we had the Permian catastrophe. At the end of the Permian, all of a sudden the climate warmed up dramatically to about the highest point it's ever been. And species went extinct in droves in this particular time. And these times here, like in the Precambrian and also the end of the Ordovician period, it's called the icebox Earth, or when it got extremely cold, possibly freezing much of the oceans as well as the land masses. So this was extremely cold, and it's very hard to explain that. The only two explanations I can think of would be that the Earth had a ring system like Saturn for a little while, and it would cause a shading effect. Saturn is known to be well shaded by its ring system. Could the Earth have been similarly shaded because some body, some celestial body may have come so close to the Earth that it just blew up and created a ring system around the Earth. The other explanation would be that the solar system went into a very, very dense intergalactic cloud, such as the one that you saw in the very first photograph here. Some of those clouds get very, very dense and they can obscure the sunlight. So that's a possibility too. Other possibility? Extraordinary volcanic activity, creating a tremendous amount of aerosols that just stop the sun from getting through. But it's hard to think of it happening on that long of a scale. But nonetheless, these cooler regions, these cooler periods of time did happen back then. Very difficult to explain. We can explain this simply because of the currents, the oceanic currents being forced into the mode that they're in now. Okay. Now, climate on the century and decadal scale. This is a short scale. This is what we're very concerned about now. This is the mechanism that causes it. Okay, it looks a little confusing, but very simply, the sun, and we have the nucleus of the sun here, this is the center of the sun, and this, by the way, represents the very edge of the sun, the so-called limb of the sun right here, is forced to go around the center of gravity of the solar system. And as it does so, sometimes you can see it, the center of gravity is within the limb of the sun, and sometimes it's pretty far out. And there's a differentiation which develops because of this. When the center of gravity is fairly close to the center of the sun, then the sun is moving around that center more rapidly. And when it's farther away, it's moving more slowly. Now, is there a consequence to that? Yes. It's sort of like when you see a figure skater at an ice skating event, and she's spinning around and her arms are out like this, and then she draws her arms in closer and closer and closer, she spins up, and she's going faster. She's not exerting anymore, but she is spinning faster because she's not having to transport it over such a big distance. And we call that conservation of angular momentum. So if she draws her hands back out again, she necessarily has to go slower again. What's happening here? Well, the sun is rotating at a specific speed. But if it's farther from the center of gravity of the solar system, then the sun's moving slower around that center, and the sun's rotation then, in response to conserve angular momentum, will necessarily speed up. So the sun's rotation, which drives its magnetism, remember it's 11,000 degrees even at the surface, it's almost 28 million degrees in its core. You have all that hot material, and it's spinning around very at this considerable rate of speed. So, but it does change. That will necessarily change the magnetic effect that the sun has. Magnetic effects change the temperature of the sun's atmosphere. The more active it is, the hotter it is, and the more it's able to radiate, especially in the high energy frequencies, such as ultraviolet light, that which gives you sunburn, and also even in X-rays as well. This radiation increases when the sun is active. So here we see year by year. Here's the year I was born. Okay, and the center of mass is constantly changing with respect to where the sun is. Now, what does affect where the center of mass of the solar system is? Okay, it happens that the outer gas giant planets, such as Jupiter, Saturn, Uranus, and Neptune, are the ones that affect it. And if they're all lined up in one spot, and they can be for a long time, remember that Neptune takes a full 165 years to go around once. Uranus is just about exactly half that, at 84 years. So twice a Uranian year is 168. It also happens that 14 Jupiter revolutions is very close to 166 years. So if you can line them up in that particular pattern, that's going to keep the center of gravity of the solar system very far from the sun's center. Now the odd one out is Saturn. which doesn't line up in any particular rhythm except every 5th time that the other planets line up. So it takes 5 different lineups of the other planets, and that takes 830 years for one to another. And they never line up exactly the same each time anyway, but there's a particular rhythm that's going on there. So this is the effect of magnetic characteristics of the sun. Again, how much it radiates, especially in the high frequency end of the spectrum. And there's the sun. This, I believe, is November 4th of 2003. And it had a tremendous eruption on the limb there. It just went ballistic. This thing, they couldn't measure it. It went off all of the charts. Is the strongest one by far in modern times. Had it been aimed toward the Earth, it would have fried all our electrical systems. It just would have. Just 1 week earlier, when it was over here, this region was over here, it would have just fried us. Now, this was taken from a spacecraft called SOHO, the Solar Orbiting and Heliospheric Observatory. It's 1 million miles closer to the sun than the Earth is, and it stays at that very stable so-called Lagrangian point. Because it should go faster, being in a smaller orbit around the sun, but the Earth is just at that distance where it can keep dragging it. So it stays at that one spot. It's a gravitational balance point. So it's always 1 million miles closer to the sun. And we can get images like this from it. This is using a very special filter. But you can see the filter was completely overwhelmed by that flare. And this is what it looked like with one of the other cameras. You can see, this is, there we go. This here is a simulation of where this actual edge of the sun is. So the sun would be here. This is what they call an occulting disk, to make sure that the camera is not completely fried by the sun's light itself. And this is the shower of subatomic particles coming out of the sun at a prodigious rate. Now, to give you an idea of the scale here, remember that picture of the sun earlier, how small the Earth would be by comparison. The Earth would be about 1/4 the diameter of my green laser here. So, the Earth is a target, folks.
Dan?
Yes.
What wavelength causes the most warming of the Earth's atmosphere when we have events like this?
Probably UVC, which is the extreme ultraviolet. That's the ultraviolet that ozone stops completely. Okay. Fortunately, because a 5-minute dose would be fatal. Right. Okay. Now, this is a graph of the last 1,000 years of climate, as determined through various various lines of evidence. The last 1,000 years in Europe, the Intergovernmental Panel on Climate Change published something similar to this in their first report back in the early 1990s. And it showed these ups and downs. Okay. This is the important one, the Maunder minimum. Yeah. And it was very, very cold back then. And this is the so-called Dalton minimum, where if you read the Charles Dickens novels, London gets cold, has snow. But after that, London wasn't getting snow anymore. But back then, back in the Maunder minimum, this is the 17th into the early 18th century, at this particular time, there was ice skating on the Thames River in London. You could ice skate on it, yeah. And this was also the time of the writing of the story about Hans Brinker and the silver skates. Hans Brinker couldn't do that today. So there was considerable change in the climate here. Of particular note is the Viking era, as the Vikings were now able to take advantage of extra warmth, and they went to Greenland and to Newfoundland, which they called Vinland, because they could actually grow vines for grape growing there. So there have been changes, and this is what we call on the decadal scale. It just so happens that the arrangement of the planets now is much the same as it was then. Remember 830 years? That's just about the gap here. Yeah. The planetary alignment, allowing for the Earth or the Sun to rotate faster. This subdues the magnetism coming up from the upwelling from the center of the Sun. We call this convection. The convection, which is a very, very fast motion in the Sun, again, because the inner core is almost 28 million degrees, the surface of the Sun 11,000, it's sort of like watching when your pot of boiling water on your stove is happening. The bubbling comes upward. You have motion of the heat coming up to the top, and then the colder water comes down from the surface, goes down. That's convection. And it happens on the Sun. That's what generates its most productive magnetic effects, is that motion right there. But if the Sun's spinning a little faster, it will tend to subdue that. And it can do it, like I said, for considerable periods of time. Also to note, in the modern era, it just so happens the planets lined up in the late 1970s in such a way that the Voyager spacecraft were able to do a little bit of gravitational boosting. First past Jupiter, then past Saturn, then past Uranus, and then to Neptune. Well, the only other time we could have done that was back in the medieval optimum. So our spacecraft that could do this came at a very, very fortuitous time. Yeah. Kind of interesting the way that works. Okay. The medieval optimum. Let's examine that. Viking explorations and settlements. We can still see their farm implements in southwestern Greenland. Can't farm there now. It's very, very difficult to. There's a very, very short growing season there. So the Vikings were able to do this with impunity, actually. And of course, they did raiding at this time. In fact, there's still a prayer, I think, still in the churches of Western Europe, called "From the fury of the Norsemen, deliver us." They still say that, right? Because the Vikings were so fierce. There was English wine, not only English wine, there was Scottish wine, and it was considered by the journals of the time to be superior to the French wine, even the Italian wine. And in Germany, they could grow olives. Well, you got to go down south to Greece to do that nowadays. And Italy, you can't do that now. Now here's a guy who made a connection. It was a little over a century ago. This fellow here, Edward Walter Maunder, was the director of the Royal Greenwich Observatory just outside London. This is where we have the prime meridian marked off. And he noticed that the astronomers of the 17th and into the early 18th century were not noticing any sunspots. Now when Galileo first observed them, there was a fairly considerable number of them. But after he passed on, a couple of other astronomers, notably Cassini and Huygens, were able to also detect sunspots, but they noticed them almost completely disappearing, maybe only 5 or 6 in a year, whereas sometimes you can see a couple of hundred of them in any one day. So what happened to them? Well, sunspots happen to be markers of solar magnetic activity. I'm happy to say that it was back in 1908 that a member of the Chicago Astronomical Society was the first one to prove that that was true. His name was George Ellery Hale. And he was the first one to prove that there's extra magnetism at sunspots. So it's a, it's a measuring stick for solar activity. So you have rare sunspots in the heart of the little ice age. So there's room for skepticism. Were they just not able, did they have equipment that couldn't do it? Well, actually, Cassini and Huygens not only discovered the rings of Saturn, that they were actually rings, they were actually able to check out some of the moons going around Saturn. Well, if you can do that, you can certainly see a sunspot. There's no question about that. But there are other lines of evidence here too. Again, frost festivals on the Thames River. That's where London Bridge goes across. But people walk out on the river because it was so icy. The master stringed instruments, the Amati family, the Stradivari. These families were making what are still the best stringed instruments: the violins, the violas, the cellos, the guarneries. These are the master stringed instruments. Why? Because the wood was denser during the Little Ice Age. That's all it was. We can't duplicate that nowadays because it's not that cold. That's why. Also, there were no aurorae during the Maunder minimum. Maunder, when he researched this, found that the journals of the time were noting that the elderly were beginning to see this glow in the night sky that they recognized from their extreme youth, almost 75 years earlier. They were seeing the aurora again. Even on our show called Arctic Light at the Space Center, it says even in northern Scandinavia, they weren't seeing the northern lights. So they were very, very scarce. Again, this is an indicator of low solar activity. Oh, I'm going to confuse the socks off of you now. A star like the sun is called a G star. There's various classifications. There's O, B, A, F, K, and M also. The ones that are O, B, A, and most of the F stars are actually too massive to allow an Earth-like planet going around them. Well, I shouldn't say that. They can have an Earth-like planet going around them, but there's a couple of problems with them. First of all, the amount of ultraviolet coming out of them is so strong, it'll be very difficult to get life going because it dissociates hydrogen from carbon, and that's a problem. Also, they don't last long enough. The more massive stars use up their fuel so quickly, life would have a very difficult time evolving to current mode or developing the way life did on Earth. I'm going to use the word developing. Evolving is sometimes a little bit misused of a term. But in any case, though, these stars are being studied at Mount Wilson Observatory by a fellow named Olin Charles Wilson. That's why they're called OCW. Now, why was he doing this? He was using the big telescope at Mount Wilson, which, by the way, George Ellery Hale, the guy who discovered the solar magnetism, was the guy who was the inspiration behind that observatory. He was the one who secured the funding for it. And what they were doing was they had the understanding that the ability to detect planets going around other stars was now coming into being. The technical means of being able to do that were now such that maybe we ought to study these stars in detail, because these would be the stars most likely to have Earth-like planets, and that's kind of like the holy grail of the whole thing. If you can find stars like the sun, maybe you're going to find planets like the Earth going around them. So Wilson decided to take up a thorough study of these stars. Stars like the sun, in other words. And not just our sun, okay. So there are other stars that have magnetic characteristics. But it turned out that by studying them with polarizing filters, they were able to notice that some were much stronger magnetically speaking than others. And those that had the stronger magnetism were slightly more radiant than the stars that did not have the strong magnetism. And they found that actually they could fluctuate back and forth. Should go back to the previous slide. Wilson turned over his work when he retired to other astronomers, and they continued his work, and they were the ones who found that in fact these other stars, like the sun, were varying in their output. And it seemed to correlate with the strength of the magnetic field. So these stars were changing on a decadal and a century scale. And they had enough of a sampling to be able to see that was happening. So an active sun actually acts as a cosmic ray shield. When there's stronger solar activity, especially the solar wind, and it gets stronger as the sun gets active, you end up with a shielding of cosmic rays. Well, cosmic rays, what do they do? All right. It just so happens that the skepticism about whether there were a few sunspots back during the Ice Age was settled by tree ring data. Botanists studying trees that lived for millennia, like bristlecone pines found out on the west coast. These trees lived for many, many centuries. And by checking out the tree rings, they're able to find that carbon-14 was considerably greater concentrations during the Little Ice Age than either during the medieval optimum or current day. So the sun was more active back during the medieval optimum, more active today. And during the Little Ice Age, very, very strong carbon-14, suggesting the sun was not keeping the cosmic rays out. The only source for carbon-14, by the way, is cosmic rays. Carbon-14 can't last very long. And we know that it has to be replenished. So it's by cosmic rays that this actually happens. And there's another element which shows it too. Beryllium-10 can be found in ice cores. And again, it's much stronger signal during the Little Ice Age. When you look into the cores, the ice cores themselves, coming from out of either Greenland or Antarctica, you can tell that beryllium-10 is laid down a lot more during the Little Ice Age. Ultraviolet radiation appears to be the #1 effect of variation in solar output. Ultraviolet seems to vary quite a bit more than the radiant energy that we see as visible light. So when you have an active sun, you have an expanded atmosphere. This is one of the things that happened during the 70s when the U.S. had a spacecraft called Skylab in orbit around the Earth. And the sun was relatively subdued back during the 70s, but as it suddenly shot up in activity toward the end of the 70s, the atmosphere expanded and Skylab began to rub up against it and crashed down to the Earth. And we lost it. Okay. So there's a terrestrial carbon thermal link. Or is there? Let's take a look at it. Remember remember back when I pointed out the temperature of the Earth? I went up and down. Well, here superimposed against it is found basically by tracing out the residue, the fossilized residue of corals and various other creatures of that nature. We can also find out how much atmospheric CO2 there was. See, we didn't have corals until 570 million years ago. That's when they started. So now we have the trace for determining how much carbon dioxide is in the atmosphere. Look at how much more there was then. And even though it's still very high, over 4,000, we still had an icy Earth. A dip down here again, corresponding with this dip, came up again. But there's no exact correlation between the amount of carbon dioxide in the atmosphere and the temperature. It's wildly swinging all over the place here. So here, oh, by the way, it's noting all these particular geologic eras and epochs and periods. Notice 2 million years. That's just a black bar there. That skinny black bar is the last 2 million years. See? And the temperature of the Earth had gone down. That's when continental glaciers began to really get accelerated. And they would come back and forth depending on the oscillation of the amount of eccentricity of the Earth's orbit. So it became sensitive to that fluctuation. Before that, it wasn't sensitive to Milankovitch forcing, the forcing of the axial tilt, or the other forcings such as the eccentricity variation or the precession effects, because the ocean's currents were able to move through the equatorial regions with impunity, so that they stayed warm. You didn't have the cold oceanic currents that we do now. That's why this era was able to stay so darn warm, because there was no interference. But tectonic effects crunched the Americas together, and you have this dip. But so was there a dip in the amount of CO2 in the atmosphere. Now you see a dip here too. Notice that's the Carboniferous period. There were so many trees back then, they sucked out all the carbon dioxide in the air. Same here. The Earth is much more forested again compared to other times in the past. So that it's the forests that are sucking out the carbon dioxide.
Well, that's interesting, because every time, well, not every time, but for years you would hear talking all the rainforests, they're disappearing, and in 10 years they will be gone. And if that's the case, then there should be all kinds of carbon dioxide.
That's exactly right. Yeah. So, should we go through carbon taxes? I would prefer that you buy forest land near Cremona, because if it gets colder, you can start making those Stradivari and Guarneri violins again. See? And you get rich. Try stock in ice skate manufacturing, all the winter sports too, and heavy coats. Right? So, if I were a gambler, that's what I would be going into. So if they say it's just us humans, don't let them kid you. Okay? It's not the case. All right, any questions? Yes, Jim?
Well, the obvious question of all, which I think you were just hinting at, is what's this say about artificial global warming of the kind where we have unwanted emissions from factory, and what actually do we expect the climate or the weather to do over the next 100 years or so?
Well, you notice if I can go back a few. Let's go back to the actual graphic that I had. Where was that? Was it that one? Yeah. Yeah, this one. Okay. Here the eccentricity of the Earth's orbit having this effect. Okay. The changing eccentricity. We see that this was an interglacial period. 110,000 years later, this one is. 110,000 years later, this is one. Okay. All right. Now, we can see this in the geologic record. In an ice cores taken out of Antarctica, it was noticed that the carbon dioxide was going up and down with the temperature. But that was in 1990. In 2003, when they had better instruments for analyzing these things, it was noticed that the carbon dioxide rise was about 8 centuries after the temperature rise. And as it cooled during the glaciated periods, which are marked by the dips here, during those times, the carbon dioxide is getting sucked into the ocean again. But it's, again, 8 centuries later. Now, you know that a gas will dissolve in water much easier when it's cold water, than when it's warm water. And it's the opposite, of course, with a solid like salt. Salt likes to dissolve in hot water, not so much in cold water. But a gas is the opposite way around. In 2003, they did notice that the carbon dioxide was following the temperature changes, not causing them. So that you had, so in other words, the cause and effect was mixed up. But for those 13 years between 1990 and 2003, everyone's saying, oh, well, look at what happened. You have the temperature going up and down with the carbon dioxide, and carbon dioxide is a greenhouse gas. Oh, what are we going to do? It must be that the carbon dioxide is forcing the warming or cooling, depending on whether it's coming out or coming or going in. So if we add carbon dioxide to the atmosphere, we're going to cause a problem. But actually, we don't, because it turns out that if you, well, let's take the example of a greenhouse. I go to greenhouses all the time because I like to do gardening, and if you look at the glass, it's only like 1/8 of an inch thick. Now, if we double the thickness of the glass, are we going to have a more effective greenhouse? We changed it. Every time you change something, you change the system, right? Actually, you don't. It doesn't. Carbon dioxide is such a strong greenhouse gas that all you have to do is have about 160 parts per million, and it's going to cover the entire heat trapping that it's ever going to do. Even at that point, we know that the Earth has always had at least 250 million parts per million, because there are a lot of plants that exist today that would have gone extinct because they breathe in carbon dioxide. They relied on at least 250 parts per million all this time. So therefore, the Earth has never had less than that. Or otherwise, these plants would have gone extinct.
I suppose another interesting one is, how much factory activity would it actually take to overwhelm the natural global system? Has anyone tried to figure it out?
It would, the amount that would take to actually try to even dent it, at least a little bit, would have so much aerosols going into the air that it would get so dark the sun's light couldn't penetrate. Now you have cooling instead of warming.
So it may not be physically possible to...
Right. It wouldn't be physically possible to do it. Again, go back here. Look at how much more carbon dioxide there was in the atmosphere in ancient times. Well, far prehistoric times. Yet the temperature is only loosely connected to it.
My other question, what's the weather really likely to do over the next century as a function of climate change?
My SWAG, S-W-A-G, or scientific wild-acred guess, would be that it'll get cooler rather than warmer.
And are we going to a real glacial age or just some minor event?
Well, if we're going to a glacial age, the Cubs better hurry. Because there'll be no more Wrigley Field.
Cubs better get their act.
Yeah, they better do it quick. Come on, guys.
Yeah,
Right.
I've seen we're on the right track.
Question.
Yes.
What would you say is the, if at all, the strongest development of facts analysis conclusion that the global warming advocates have ever put forward?
simply the fact that there has been warming. But that's simply, it appears to be a rebound from Little Ice Age. And enhanced solar activity.
Well, that's simply stating a fact and drawing a conclusion.
Yeah,
What analysis,
Yeah.
if any,
Yeah,
do they
that's
have
right.
to bridge the fact and the
It's
conclusion?
it's really difficult for them to do it because I'm not sure there's certainly no double-blind experiment in this case at all.
There, of course,
It's
there
just not happening.
Well, it's,
You don't have that. It's taking what originally was speculative musing by scientists such as Fourier, Arrhenius, these people who were postulating the greenhouse effect of the atmosphere. Well, the water vapor is doing 90% of it. Excuse me. Carbon dioxide does most of the rest. There's methane, which does some too.
some hydrogen.
Right. There's other trace gases that are doing it, and they're strong greenhouse gases. But they're so strong that you only need a little bit of them, and they do all the trapping that's ever going to happen from the amount that's there. By the way, I promised I would show you the telescope that took that initial photo.
Pardon me.
It's that one, yeah.
Again, have they stated an analysis? Or have they simply stated a fact and a conclusion?
They keep coming up with formulas about the extra trapping of, I think it's 3 watts per square meter of energy that we have, that's a greenhouse trapping. And they say that would necessarily increase with extra carbon dioxide. Okay? And you can run through the math day in and day out and find that doesn't work. Now, 4.5 years ago, I was in a campus debate at Triton College about global warming. Now, that was April of that year, April of 2007, and the month before, at the regular meeting of the Chicago Astronomical Society, there was a physicist who was a speaker from the University of Chicago. He had one of his colleagues along with him, and I mentioned at the meeting that I was going to have this debate. And this one fellow from the physics department said, we're so happy to hear that you're going to do this, because especially in the math department, these guys are complaining they can't speak their minds because the grant foundations that keep the University of Chicago going won't have it. They won't have people saying that global warming isn't happening. But it's the mathematicians figuring out that when you have say greenhouse glass, the glass of a greenhouse, you have the infrared coming up against it. Well, it managed to get trapped just in the first few layers of glass crystals. It doesn't even need the 1/8 of an inch thickness to trap it all. It's trapped at a logarithmic rate initially, then arithmetically, but then it drops to an inverse logarithmic rate. And it's the same as true as in the atmosphere. It drops to an inverse logarithmic rate. That's why doubling the CO2 in the atmosphere, according to a famous scientist from MIT, it'd almost be hard pressed to even get 0.2 of a degree Fahrenheit out of that.
All right. In other words, about 1/10 of a degree centigrade.
Yeah.
All right. By what analysis did the mathematicians conclude that the increase in CO2 would be would result in no more of an increase in temperature than an increase of the thickness of glass in a greenhouse would increase in temperature? By what analysis did they? Again,
it's simply taking the initial amount of trapping, which again is a logarithmic rate.
All right.
Okay. And finding what happens by the time you get to the other side of the glass.
Well, yeah. but what about carbon dioxide? How
Yeah.
did they
It's-
deduce that the same effect would be
Yeah,
produced?
because it's a greenhouse trapping.
So in other words,
It is a trapping, yeah.
Okay, was this an assumption, or did they have data which showed that CO2 would do the same thing as the glass?
Yeah, it appears that they did in fact analyze it in exactly the same manner. Now, I don't have their direct word. I only have the word from this physicist who was at this meeting,
Okay,
that they were saying that it's the mathematicians who are figuring out that it's not happening.
okay,
And they're very upset because they can't get the word out.
all right.
They're censored. And this happens at virtually every academic institution. Those who really don't believe it are censored because,
May I have your attention, please? The time is now 8:30 and the library closes at 9 p.m. Please be prepared to conclude your library visit within 30 minutes.
You're trapped.
Thank you.
Dan,
yes,
how soon should the predominant cooling start to dominate again?
well, right now it probably would be starting to cool already, except for one thing. Are you familiar with what's called the Danjon scale?
How'd you spell that?
Danjon. It's the relative brightness of the moon during total eclipse.
Uh-huh.
Okay, 0 is
Not
a
really.
bright black eclipse, and 4 is a bright eclipse, and everything in between. It just so happens that the brightness of a total eclipse of the moon, because the refraction through the atmosphere of sunlight gives that coppery color, that reddish coppery color, because you're looking at all those sunsets, so to speak, around the Earth. That refraction allows the moon to still be seen during totality. Well, the amount of aerosols, especially in the stratosphere, will determine whether it's very dark or very bright, relatively speaking. And there's been very few volcanic aerosols in the last, say, at least decade. The last time it was really filled with aerosols was after the eruption of Mount Pinatubo in 1991. And it's interesting to note, if you turn on your weather radio or go into the local weather archives, it happens that all the low temperature records for this time of year occurred in 1991. It was immediately after the ash cloud from Mount Pinatubo was surrounding the Earth, and it stopped the sunlight from getting through. So the next time we have a Pinatubo-like eruption,
What
we're
about
going to
that
cool off.
Unpronounceable volcano in Iceland.
Oh yeah, right.
That was in 2000.
That one didn't produce anything close to Pinatubo.
Okay.
Yeah. The three biggest ones were Mount Agung in 1963 and Mount El Shishong in Mexico in 1983. No, 1982, yeah. The one in 1963 produced the blackest eclipse in modern times. I saw it. I was a member of my high school astronomy club at the time, and the temperature was 11 below, and the wind was never less than 20 miles an hour. And there's 7 of us guys out there looking at this thing in the midst of that. And the moon just disappeared. It just completely disappeared. It was stunning. In fact, a couple of the guys were trying to photograph it, and the film froze so hard in the cameras that it broke as they advanced the film. Yeah, it was that cold. And when I got home, that was the longest I ever slept without waking up. I went to bed at 7:30 in the morning, and I woke up at 9:30 that night, 14 hours without waking up. I was really dead tired after during that. Anyway, real quick, I promised you the camera, the telescope that took that shot was this one right here. It's just a 6-inch diameter glass, and it had this camera on it. The camera was switched over to this scope. This scope is also used for photography. Now, the scope that you saw in Florida was 16 inches in diameter, the glass. And this one's 10-inch and this one's 6-inch. So they're smaller scopes, but they're in compact units, and the curves on them are such that it concentrates the light very hard, very rapidly, so that it's able to get two things: a wide field of view and a very fast photographic effect. So you don't have to expose terribly long. Nonetheless, there was a 3-hour-long exposure. Okay. The catch is that you have to have a mount like this one. This costs $12,500. That mount, so it could keep track. Okay. That was the catch. But we found out that we could make optics using reflecting telescopes, mirror telescopes, such as the one Isaac Newton was first to invent, and get very, very sharp images. Here's another one. And going back to the doc, when Mars made a super close approach in August of 2003, notice that against Hubble, he had nothing to lose. He had resolution that was very comparable to a telescope that was 66,000 times higher up and cost 80,000 times more to build. You know. Again, that little white 6-inch scope took that shot. Now, that's the so-called flaming star nebula. Other gas clouds in space. Again, our solar system was born from a gas cloud like this. And we can see that other star systems are forming here. And that's one of my very favorite shots. Boy, that's a pretty region. In the constellation Perseus, the region where the Perseid meteors emerge from every August. And what I like to call the bug-eyed monster. There we have it. Yes?
Can I ask one last question?
One last question. Go ahead.
Is the so-called Mayan calendar in any way related to any of the material here tonight?
It only has a relationship in that the precession of the equinoxes has forced the first moment of winter to line up very closely to the center of our galaxy. That's the one thing that has happened. But it's always
practical matter then, no.
But, yeah, it's a practical matter, no, because it's always been, in the last several centuries, it's all been close enough to create some problem. If it's ever going to have a problem, it already would have happened. So that's the only relationship this has to the Mayan calendar. Sorry.
Well,
So,
not everything
no,
can be true.
on the solstice next year, the Earth will not come to an end. Okay, you're safe.